Kumar for his presentation on Indian experience in manufacture of thorium-based fuels. Mr. Shri Arun Kumar is presently the director of the Nuclear Fuel Group in BARC. He has been associated with the fuel fabrication of nuclear reactors and has vast experience and expertise in nuclear fuel fabrication. And Mr. Arun Kumar, the floor is yours.
Thank you, Mr. Chairman. I am going to talk on Indian experiences so far in the manufacture of thorium-based fuels. As most of you are aware, thorium is a very important material, nuclear material, in Indian context because of the limited uranium resources which our country has, and for continued sustainability of the nuclear power program of this country, exploitation of nuclear energy from thorium resource is of big importance. And in this respect, various type of development works have been taken up in India, right from mining, manufacturing, reprocessing, and even waste management. Of course, till now we have not come to the stage where a thorium fuel reactor is in position, power reactor I mean. We are having one research reactor, but power reactor wise, till now we have not set up, but we have understood the technology and the science behind thorium. And in very near future, this program is going to be launched. And you must be aware that already India has designed one advanced heavy water reactor system in which thorium-based fuel is going to be used. So in that context, we have done whatever work we have done, I am going to present. Straight away, I am coming to the issues, some of the specific issues which are in thorium fuel manufacturing. The thorium oxide powder, it is derived by oxalate precipitation route, and it has got a plate type of morphology which is having its effect in the fabrication of the fuel. Then thoria being a perfectly stoichiometric compound with very high melting point of the order of more than 3400 degrees centigrade, this requires higher sintering temperature. And the recovered U-233 by reprocessing from thorium fuel from power reactor is always contaminated with U-232, whose daughter products bismuth and thallium are hard gamma emitters. This is also having effect on the fabrication technology in making this fuel. And because of this bismuth and thallium, this requires to be fabricated in shielded facility. That becomes a requirement, unlike uranium oxide fuel. Then reprocessing of thorium-based fuel, it has to overcome issues like dissolution of a spent fuel, because thoria is a very stable material, and its difficulty in partitioning due to single oxidation state, and third phase formation issue during reprocessing. Now coming to the fabrication and irradiation experience, I will come to the fabrication afterwards, but just to give you a glimpse of what we have done till now, we have started with thorium metal irradiation in Cyrus reactor, that is what we call J-rods. Thorium oxide fuel assemblies have been irradiated in our Dhruva research reactor. Thoria fuel bundles have been used in our PHWRs for flux flattening. Thoria fuel assemblies have been used in FBTR blanket region. Then number of experimental irradiation of thoria-based MOX fuel pins have been done. First one was BWR size, short length, TAPS element. They were irradiated in Cyrus reactor. Then PHWR size pellet encapsulated in PHWR type of size. They were irradiated in again in Cyrus reactor, and then some HWR type of pellets. I am talking from shape point of view and size point of view of having different type of fissile material like plutonium and LEU. They have been irradiated in Dhruva reactor. Coming to U-233 recycling, the experience which India is having is, first is one research reactor, Purnima 2, with liquid fuel, where fuel was uranyl nitrate solution was used. Then Kamini type of plate fuel containing uranium aluminum alloy, it is in use in this reactor even now, and it is based in Kalpakam. And then some short length PFBR fuel assemblies having uranium plutonium MOX fuel has been irradiated in FBTR for proof testing of PFBR design. Of course, in PFBR it is uranium and plutonium MOX, but here U-233 has been put to get the similar heat flux in FBTR neutronic conditions. So fuel cycle options for using thorium in water-cooled reactors are thorium LEU MOX, thorium plutonium MOX, and thorium U-233 MOX. And fuel manufacturing technology varies for each of these options. When we come to thorium LEU MOX, LEU is nothing but less than 20% enriched uranium. This is made in the similar conventional powder metallurgy route, using the same route, and you have to mix the material with the LEU oxide powder, granulate it, pre-compact, compact, and sinter. Route basically remains same. However, there are some issues because of its platelet type of configuration, that pellet morphology. The flow sheet necessarily requires some attrition mechanism to change the morphology of the powder so that the powder becomes compactable and good sintered pellets are obtained. Then because we are using LEU, it will be associated with some amount of criticality issue. So we have to take cognizance of that. And because of the presence of LEU and thoria, this being the material in the fuel, there are some specific radiological issue when we compare it with natural uranium fuel fabrication. This commercial LWR fuel fabrication plants are licensed up to 5% of enriched U-235 fuel. And when you go for LEU fuel, then this thing is of the order of 20%, something maybe 19 to 20%. So because of this type of enrichment, some radiological issue crops up. And then because it is slightly more enriched uranium, there will be issue of criticality which has to be taken care during fuel fabrication. And because of these, this limits the size of the equipments and thus the throughput of the plant. And in many instances, especially for wet type of operation, the batch type mode of operation becomes more preferable compared to continuous mode, which is normally used in uranium oxide facility, especially in wet processes. Coming to the radiological issue associated with thorium, the thorium decay chain, finally, this again gives you bismuth and thallium, the hard gamma emitters, and in the natural thorium, this is the equilibrium concentration of thorium-228, which is the precursor for getting this bismuth and thallium. So naturally, this thorium fuel, because of the agings, when you have separated out thorium oxide after precipitation, if it gets aged, this dose level during material handling is going to increase, unlike what happens in UO2. Another thing, when you enrich uranium, the U-234 content also goes up. This you compare with natural uranium to LEU, it goes up. And this in turn, increases the specific activity of the material 18 times more than natural uranium in terms of alpha. So this gives you this higher activity issue which has to be tackled during fuel fabrication. Another problem is in the thorium fuel fabrication, some radon gas gets generated which has to be handled carefully by careful design of ventilation system so that it gets converted into the solid product. Its decay product is solid and it gets filtered before the air is released in the atmosphere. So a special type of ventilation design is required. This again, what it is showing you, this is the UO2 powder morphology. This is the morphology of thorium oxide powder, and this is after milling. This type of powder is more compactable. This shows the grain morphology which we get in a sintered thorium pellet, thorium oxide pellet, MOX pellet, and this is the homogeneity which we can obtain by idea about homogeneity which we can obtain by alpha auto radiography. Thoria is having very high melting point. So it requires very high sintering temperature also compared to UO2. If we sinter thoria at 1600 degrees centigrade, in our laboratory we have got density only up to 80% or so. If we dope it with dopant like MgO to introduce, this is to facilitate introduction of some amount of defects to improve the sinterability of thoria powder. We have got 92% at 1700 degrees centigrade. At this temperature, with UO2, we could have got 95 to 97% density. But here, even with magnesia addition, we are getting only 92%. If we add some amount of niobium oxide also, this is another dopant, we are able to get near about 94% density. This slide I have just prepared to tell you that you appreciate the fact that thorium is not having as good a sinterability, thorium oxide, as UO2 has. Coming to manufacture of thorium-plutonium MOX, the issues related to thorium that most of us we are aware by now, that is radon problem and higher radiation dose. Apart from that, if you introduce plutonium, the specific issue related to plutonium also has to be tackled. Plutonium is a very radiotoxic material and it needs handling in globe boxes. This type of globe boxes are used for preparation of any MOX fuel which is having plutonium, whether it is UPU, whether it is thorium PU. And when you go for globe box facilities, globe box restricts the size of manufacturing equipments. So naturally the throughput. This restriction is of greater concern as the thorium-plutonium MOX fuel for thermal reactors, it will require tonnage quantity of fuel. And because of the globe box handling, the job increases quite a bit. The footprint required for the plant will increase like anything. Coming to manufacturing aspects associated with thorium U-233 MOX, U-233, it is always associated with U-232, giving daughter products which are hard gamma emitters, requiring shielded facility. Shielded facility, I mean hot cell type of fuel fabrication. And it should be leak tight also, because uranium is having higher, U-233 is having higher specific activity as well, apart from hard gamma emitters. This is the same thing. So some of the techniques which has been studied in BARC are listed here. Powder pellet route, this is the conventional route by which UO2 is made. This type of flow sheet, if we go for, we will require fully shielded facility. Wherever this U-233 is there, everything has to be done in the inside the hot cell, all the processing. Sol-gel microsphere pelletization. This is first gel microsphere is fabricated, which is having both thorium and U-233, and then it is compacted and again pin is made. This also requires fully shielded facility. One goes for this technique because this type of powder, sol-gel powder, they are free-flowing powder. Automation of the plant is easier. And this process doesn't require the step of pre-compaction granulation, which is required in powder pellet process, conventional powder pellet process. Then another route which has been tried is pellet impregnation, where low density thoria pellet is made first in a non-shielded facility, and then it is impregnated with U-233 solution inside the hot shell, and then it is sintered and it is converted into pin. So this will require partially shielded facility. Up to thoria, low density thoria pellet fabrication, it is in non-shielded facility. Then coated agglomerate pelletization is another route which has been attempted. Here, thoria agglomerates are made by various techniques, and afterwards the U-233 is coated above this agglomerates in a shielded facility. So up to agglomeration, up to agglomerate making, it can be in non-shielded facility, and rest is in shielded facility. Thorium LEU MOX, already I have discussed. Conventional UO2 type of fuel fabrication flow sheet with some amount of shielding because of thoria giving some amount of gamma. And then thorium plutonium MOX glow boxes. This is sol-gel preparation technique. It is indicated here how the gel microsphere is prepared. Then it is calcined, pelletized, sintered, and you get the dense pellet. Pellet impregnation. Here the low density pellet, thoria pellet, it is impregnated with the uranium solution, U-233 solution, and then it is sintered. And so all these experiments have been done. Another process which has been studied is gel impregnation technique, where the microsphere which has been made by that earlier technique what I was showing, it is impregnated with the U-233 solution, and then it is converted into pellet. Coated agglomerate pelletization. Agglomerates are made by pre-compaction granulation or extrusion or sol-gel technique, and then they are coated with U-233 oxide in a shielded facility. These are some of the photographs which shows this particular coated agglomerate pelletization process, various products in various stages. These are the thoria spheroids. Then it is coated with uranium oxide. These are the green pellets. This is the microstructure which we obtain in this sintered pellet. This is the same thing, whatever I have talked. Now, another major issue in fuel fabrication is the recycling of the reject in the thorium fuel fabrication. Thorium is a very, as I have earlier told you, it is an inert type of material, monovalent material. It cannot be powdered as we do in UO2 flow sheet by oxidation reduction process. It is a difficult material to be recycled in the process flow sheet. And two methods have been tried in BARC. That is, one is dry recycling and wet recycling. In the dry recycling, the process is to make powder from sintered mass, either by comminution technique like milling or if it is having some amount of UO2, then by going for oxidative reductive process, which cracks the pellet because of the presence of UO2, and then it is crushed and milled to make it into powder. However, such type of powders can be used only up to limited extent. You can see only 15% or 20%, between 15 to 20% only. We can add it with the fresh powder and get useful product. So this gives a limitation. However, this is a thing where by which some quantity of material you can recycle in the flow sheet. Some wet recycling studies have been done in our nuclear recycle group, where they have this requires dissolution in high concentration HNO3 at high temperature and addition of fluoride. And studies carried out at BRC shows that 8 molar nitric acid with some fluoride catalyst under boiling condition, it takes near about 48 to 72 hours to dissolve the material. It is quite a bit of time compared to UO2 fuel. And recovery of thorium by oxalate precipitation route and uranium by conventional ADU process has been studied from this solution. And the powder so recovered has been converted into pellet of acceptable quality. Pellet making is not much of a problem, but the problem is addition of fluoride, and this we have to become conscious about the corrosion of dissolution tank material which we are going to use there, and studies are going on. Now coming to some irradiation experience, two types of fuel clusters which has been irradiated in Cyrus earlier. One I was telling you, one was BWR design, another was PHWR design. Number of pins I have indicated in these two clusters are this. The design type is this. Burn up, what it has seen is also indicated here, and linear heat rating. This AC6 cluster, it was having thorium 4% PO2 fuel, 5 numbers. This is a empty helium pin here. And fission gas release, which was measured in our PIE facility, it was found to be only 0.5%. And fuel center temperature, it was estimated to be 1200 degrees centigrade, less than 1200. Whereas UO2 fuel of PHWR, one of the typical result, what we are showing you, the fuel has been irradiated at 15,000 megawatt, LHR almost of the same order, fission gas release is 20% compared to 0.5 in Thoria. And fuel central temperature 1700 degrees centigrade. This type of behavior means this is a very good comparative behavior which I am trying to indicate. Thoria fuel behaves much better than UO2 fuel in similar condition because of its better thermophysical properties. These things, they show the beta gamma autoradiograph of this is thoria fuel, this is uranium oxide fuel. Here, the fission product redistribution is almost not there because temperature gradient is less. Here you find there is redistribution. It's the fission products like cesium and other things, they are migrated to the near the cooler region. Thermal performance wise, UO2 fuel, you must be seeing lot of cracks here, less cracks. And this dark region, whatever you are seeing, is the porous region in the central region of UO2 fuel because it has seen higher temperature and pores are migrated inwards.
We have a few minutes left for the questions, so if you can come to the conclusion.
Look at 2 slides. Okay. This shows the defect behavior compared to UO2 fuel. This is the thoria fuel. Some type of defect in the clad has been observed here during our PIE investigation. This is the region of interest, but we do not see much of fuel leaching out from the this particular region and not much of corrosion also. But in this fuel, UO2 fuel, you can see lot of fission product migration and then the corrosion layer which is found on the clad in the case of UO2 is much higher than what you get in thorium. SW or any of persons have already talked. This is one demonstration facility which we are trying to set up. We have set up, but we are making more fine tuning in this system, and we are going to introduce it inside a hot cell to make remote fuel fabrication of thorium U-233 type. This I will skip. Coming to summary, in India, different types of thorium-based fuels have been fabricated and irradiated in different research and power reactors, right from metal to oxide, MOX, and things like that. U-233 aluminum alloy fuel has been used in Kamini reactor. U-233 has also been used to manufacture short-length UPU MOX, PFBR fuel test assembly.
Yes, I want to ask you a question about the part on wet recycling of thoria pellets. Did you also test methods for dissolution without the use of HF?
Repeat your question.
Yeah, I have a question concerning the wet recycling of thoria-based pellets. There you tested nitric acids with hydrogen fluoride. Did you also test methods without hydrogen fluoride, so without fluoride in the system?
No, without fluoride if you do, it will take much longer period than what we are indicating.
Yes, I know, but it would be interesting to see if it would be feasible without the fluoride. You did not test any...
Anyhow, I'm not ready with that data, but maybe somebody in the audience, if they are present here, they can say. But this study, what I have reported is only with fluoride.
Okay.
One more question from the audience. Yeah. Microphone.
With a response to that question of dissolution without chloride. As I mentioned in the morning, it is possible to dissolve thoria without chloride. But if you add the chloride, it helps in the faster dissolution. The fact remains that in the dissolution, when you add the chloride, the apprehension that chloride will create corrosion and all that is not much, because we also add a complexing agent which complexes the chloride. like we add the aluminum, so it forms aluminum chloride, which is not a corrosive. The question of chloride or fluoride concern is in the waste, which is getting generated, and if you have to vitrify that waste, as I said. But there also we find that the volatility, see the chloride or fluoride are highly corrosive only when they are in the vapor state. So the fact remains that when you do that vitrification, we have seen that the volatility is just 3%, which is good enough for the stainless steel type of materials. So this is the response. What is our experience with respect to the dissolution in presence of fluoride or chloride? Thank you.
And as we're short of time, I would like to thank Mr. Arun Kumar for his presentation. And on behalf of the organizing committee, I would like to present him this memo.